Welcome back. We will continue our discussion on the canonical ensembles today by considering the three important relationships that we have already discussed about. Today, I am going to first look at the importance of this particular relationship and show you that once you have a model, you will be able to find out the partition function Q. From there, calculate the Helmholtz free energy F and calculate whatever thermodynamic quantity you would like starting from a microscopic model. In the second part of this lecture, we will look at the properties of this probability Pi and the practical significance that this relationship has. So, first let us have a look at how to model the thermodynamics of a system starting from the partition function. So, this is the relationship that we already know from the derivation that I presented in the earlier lecture. So, we know that the Helmholtz free energy, which is a natural variable of the parameters T, V and N, that is related to the natural logarithm of the partition function capital Q, and here this capital Q contains all the informations regarding the microscopic states of the system. Now, let us think about another thermodynamic property like the internal energy. Now, if I want to find out the internal energy, I have made it very clear by now that the internal energy is nothing but the average energy in this canonical ensemble. So, how do I find out the average energy? Of course, by definition, this average energy is given by summation over I EI Pi, right. So, EI for the ith microscopic state, EI is the solution of the Schrodinger equation. So, this is the ith energy eigenstate and Pi is the probability that the system resides in this ith microscopic state under the given condition of temperature, volume and number of particles. Now, if I write down explicitly what Pi is, I can very easily show that this must be something like EI e to the power of minus beta EI by definition of Pi. So, this is my E bar. Now, is it possible to simplify this expression to a more usable form? For that, what I am going to do is I am going to write down the definition of Q. So, by the definition of Q, I have to sum over all possible values of I of this exponential function. Okay. What I do next, please remember that Q is a function of Q is a function of T, V and N. Therefore, or I can take a derivative of Q with respect to either T or V or N. What I decide to do here is I am going to take a derivative of Q with respect to beta, keeping V and N constant. Now, very simple mathematical treatment tells you that you can do this derivative within the summation, and what you will be left with is on the right hand side, that is EI e to the power of minus beta EI. Now, I divide both sides with respect to capital Q, giving me this as minus 1 by Q summation over I EI e to the power of minus beta EI. Now, does this look familiar? Of course, this is nothing but this expression that I have written down here. Okay. And therefore, I should be able to say that E bar is equal to minus 1 by Q del Q del beta, keeping volume and number of particles constant. But as you see that this can be further simplified, I can very easily write down that E bar is equal to minus del ln q del beta, keeping V and N constant. Okay. Now, somebody may argue that, well, actually we would like to see the derivative with respect to temperature rather than beta. So, that is pretty simple. Once again, what we can do is we start from the definition of beta. Beta is equal to 1 by kT. Therefore, what is d beta dt? It is a function of temperature, Kb being a universal constant, that is 1 by kBt square. Now, can I write down what E bar is in terms of taking a derivative with respect to temperature? I know that E bar is del ln q del beta, keeping V and N constant, and this I am going to write as del ln q del T, keeping V and N constant, into dt d beta. Therefore, if I just check this expression and this expression and combine them, what do I get? I get E bar, that is equal to kBt square del ln q del T Vn. So, this is trivial algebra, and one can have a look at the expression for internal energy that I have put in over here, and that is nothing but kBt square into del ln q del T, keeping volume and number of particles constant. Now, once you have the Helmholtz free energy and the internal energy, in that case it is very easy to find out what the entropy of the system is. Now, can you guess? Because that is only one more algebraic step, and that can be carried out as follows. So, I am looking for an expression for entropy. Now, I know that F is equal to U minus Ts, right. Therefore, I can write down that Ts is equal to U minus F, or S is equal to U minus F divided by T. I know at present U in terms of ln q, I know F in terms of ln q. Therefore, if I plug these expressions in, what should I get? This is the expression that I am going to get. Can you identify the different contributions that are coming in to this expression? Of course, this part comes from the Helmholtz free energy part, and this part comes from the internal energy part. So, as you see that if you have a model for which you can determine the partition function q, you will be able to calculate not only the Helmholtz free energy and the internal energy, but also the entropy of the system. Of course, there are other quantities which are very, very important as far as our understanding of any working thermodynamic system is concerned. So, let us have a look as to how we can calculate pressure from ln q. So, in order to do that, you must realize that I can write down df as minus s dt minus p dv plus mu dn in general. So, when I have a closed system, dn is 0. So, this term will not be there, but if I have an open system where n is allowed to fluctuate, the last term on the right hand side will be present. So, from here I can immediately write down that del f del v T n, what is that quantity? That is equal to minus p, and del f del n T v, that is equal to mu. So, if I now exploit the fact that f is equal to minus kBt ln q, I note that in both the cases I am keeping temperature constant. Therefore, I should be able to write that minus p is equal to del del V of minus kBT ln Q, and this derivative is being done under the condition of constant temperature and number of particles, and therefore, I will be able to write that P is equal to kBT del ln Q del V Tn. So, that is exactly what we have noted down here, that pressure is equal to kT multiplied by a derivative of natural logarithm of Q with respect to volume, keeping temperature and number of particles constant. Now, similarly, it is very easy to show that the chemical potential now is given by mu is equal to del del N of minus kBT ln Q, but now the constancy is maintained for both temperature and volume. Under such condition, I can take out the kT from the derivative and write that this is del ln Q del N TV. Okay. So, even if in general it is not a closed system, but an open one, in that case you can find out the chemical potential starting from Q. Now, let me take a very simple example where I have a highly idealized system where there is only one particle, okay? That is n is equal to 1, and the model, the microstate of the system is given in terms of, and the microstate of the system is given in terms of this two-state model. So, it has E1 equal to 0, only two energy states are possible, and E2 is equal to epsilon. Then the question is, can I set up the partition function of this system? We have already seen that by definition, for this system, if it is present at a given temperature, volume with n equal to 1, where for each particle with this single particle, this is the definition of the microstate, then the corresponding canonical partition function, this is going to be a function of temperature and volume, and this is given by 1 plus e to the power of beta epsilon. Okay. So, if that happens, then I can very easily write down what is, I am writing this small q instead of capital Q because I have a single particle system. Now, what is the Helmholtz free energy for this system? That is obviously going to be minus kBT ln Q, or F is going to be equal to minus kBT ln 1 plus e to the power of beta epsilon. Okay. Now, since I know things like ln Q, of course, I can find out all other thermodynamic properties, because that can be obtained as a derivative with respect to this ln Q. Is that correct? Yes. Now, the question is, if I have a collection of n particles that are not interacting with each other and that are distinguishable from each other, in that case the total energy of the system will be written as, say, something like E1 plus E2 plus E3 and so on and so forth. So, maybe let me take a simpler system like capital N is equal to 2. So, I have a two particle system. For each particle, the microstate is given like this. I have taken these two particles in the setup of a canonical ensemble, that is, my system is comprised of two such particles whose microstates are given by this two-state system. This is particle 1 and this is particle 2. They are present in a system and in equilibrium with the thermal reservoir. Now, my question is, in this case, as you understand that There may be many different states for in general. So, in this case, what are the different states? One of the typical states would be particle 1 in the lower energy state and particle 2 also in the lower energy state. Maybe so this is the lowest energy micro state for the system. Okay. So, this way I can say that the jth energy state will correspond to the say mth energy state of particle 1 plus nth energy state of particle 2. So, what is the total partition function of the system then? That is going to be summed over all j e to the power of minus beta E j. Now, this I am going to write down as summed over all j e to the power of minus beta, but E j is something like this, E m 1 plus E n 2, which means that instead of j, I will now have to sum over m and n. So, in practice, what I have now is two terms, e to the sum over m e to the power of minus beta E m and summed over n e to the power of minus beta E n, right. This is for particle 1 and this is for particle 2. Okay. But as I said, both the particles have the same underlying structure, microscopic state, and therefore, I can say that this is the single particle partition function for this two states system. So, I will be able to write that capital Q, that is equal to, this is small q 1 multiplied by, this is corresponding to the particle 2, small q 2. But basically, if their underlying microstates are the same and they are not interacting with each other, therefore, replacing these two things, I can write down any of these q i's is nothing but 1 plus e to the power of minus beta epsilon. As a result, 1 plus this, as a result, capital Q is now becoming, if I put this as small q in general, small q square. Okay. So, once again, let us recapitulate. If I have capital N particles that are non-interacting, that are distinguishable otherwise in terms of the label that they carry, like particle 1, 2, etc. But if they are microstate, they have the same microstate, does not matter which particle you are talking about. I said that they have the same microstate like this. Then each of these particles is characterized by a single particle partition function, which is 1 plus e to the power of beta minus beta epsilon. And then if these are non-interacting, and therefore, I should be able to write that the net partition function for this n particle assembly is going to be small q for the first particle, small q for the second particle, and so on and so forth up to the nth particle, and that must be equal to small q to the power of n. So, if I have capital N non-interacting distinguishable two-state particles present under canonical ensemble, then what is going to be the form of capital Q? Capital Q is going to be given by 1 plus e to the power of minus beta epsilon whole to the power of n. So, what is ln capital Q? That is going to be n ln 1 plus e to the power of minus beta epsilon, and of course, I can write down that the free energy is minus nkt ln 1 plus e to the power of minus beta epsilon. Now, from this result, you see what we started with was very simple. I had a microscopic model of my particles. these numbers were obtained from the solution of the Schrodinger equation for this kind of particle. And we found that there are only two energy eigenstates possible, one is 0, another is having some energy value epsilon. And then we asked this question that what is the free energy of this system? The microscopic model, mind you, gave you a model at the microscopic level or the atomic level or the molecular level, and the free energy is where you have 10 to the power of 23 particles together. For the sake of simplicity, we have assumed that they are non-interacting, and as a result you see that I have been able to obtain an usable form of expression for the Helmholtz free energy. Now, if I go a little farther, you will see that it is possible to talk in terms of the thermodynamics of a simple harmonic oscillator. So, let us say that I have a volume V and there is this constant volume box. It has only one simple harmonic oscillator in it, and this box is surrounded by a rigid impermeable wall. It is placed in contact with a thermal reservoir so that it attains thermal equilibrium with the reservoir at a temperature T. Then my question is, what is the canonical partition function for this single simple harmonic oscillator? The answer is Q must be equal to summation over all possible microstates of this oscillator e to the power of minus beta EV. Now, for a given simple harmonic oscillator, do I know what EV is? The solution of Schrodinger equation tells me that possible values of EV are V plus half H cross omega. So, I can directly put it in there. So, I will say that Q is equal to summation over V going from 0 to infinity, because those are the allowed values of the vibrational quantum number, then exponential V plus half H cross omega multiplied by beta. Okay. Now, I see that there are two portions in this within the summation. So, one portion is e to the power of beta H cross omega into V, another portion is e to the power of half beta H cross omega. Obviously, this term does not depend on this summation, I take it out of the summation, and therefore, I find that small q is equal to e to the power of half beta H cross omega into this infinite summation. And the moment you have some infinite summation, you should be aware that this is something that you need to evaluate if possible for this expression to be practically useful. So, in order to do that, what I will do is I am going to represent this, sorry, not n, this is V, this number as x. Okay. So, what does this summation look like then? I have V equal to 0 to infinity x to the power of V, and this I can write down as 1 plus x square plus x cube and so on and so forth. But this infinite series does look familiar and it does have an analytical result, and that is given by 1 minus x. So, if I put it back over here, what I find is q is equal to e to the power of half beta H cross omega divided by 1 minus x, which is this quantity, e to the power of minus beta H cross omega. Okay. So, this is what we have written down over here. So, now you see that for this system, if since I can evaluate the partition function, it is very easy to work out the thermodynamics from here. Similarly, when I have capital N such simple harmonic oscillators all having the same angular frequency, in that case if they are distinguishable and non-interacting, and if they are present in a constant volume V at a temperature, constant temperature T, I can very easily write down that for each of the simple harmonic oscillators, I can have an analytical expression for the canonical partition function, and then the canonical partition function for the n particle system is going to be given like this. Now, once you know capital Q, you can very easily find out the natural logarithm of this quantity and connect it to the thermodynamics. So, in the next lecture, we will see some of these very interesting applications, but before I go finish this lecture, I would quickly like to highlight the other end of what of the three relationships that we have learned in this class. So, we have learned what Pi is. So, Pi by definition is related to capital Q and EI, where capital Q is the canonical partition function, which you have already seen. Now, let me go a little farther and say that, did you notice that Pi depends only on the difference EI minus E naught? That is simply because we can set the 0 of energy to the lowest energy state and count the difference in energy from there. So, accordingly, we will see that the P of I can be written down using this kind of expression, where Pi is having functional dependence on EI minus E naught, and you are setting E naught equal to 0 in your energy scale. Now, if I go a little further and try to understand the consequence of this, we understand that in general, from the solution of the Schrodinger equation for simple systems, we always find that EI plus 1 is greater than or equal to EI, assuming that I is the quantum number that we are talking about, and this would imply that EI minus E naught will always be greater than or equal to 0. So, this typically is the way we assign the energy states. The lowest energy state E naught, that is the 0 of the energy state, and as I go from E naught, E1 to E1, E2, E3 and so on and so forth, the energy value EI that increases. Now, for the sake of simplicity, let me assume that this particular energy level, the difference in the energy level, this gap, it is uniform for all the energy states, and this is equal to kT. Okay, once we do that, then it is possible for us to have a simpler expression for this quantity EI minus E naught by kT. So, what happens if I go from I equal to 1, 2 to 3, this quantity EI minus E naught by kT, that also increases as 1, 2 and 3, and correspondingly what I can say is, if I look at this quantity which controls the probability Pi, that now is a number less than 1. And if it is a number less than 1, as I go from I equal to 1 to I equal to 3, I find that this exponential factor, it goes from about 0.4 to about 0.05. So, this number decreases. Now, this is what has been shown pictorially over here. Then this value, it increases as you go down in energy and it decreases as you go up in energy. Now, the result of all these things is that I can very easily write down that e to the power of minus E naught by kT will always be greater than or equal to e to the power of minus E1 by kT and higher energies. And the consequence is that if I follow the definition of probability, then what will happen is, if energy increases in this direction, the probability of observing that particular state, or the probability of a particle of occupying that particular state at a given temperature decreases. Okay. Now, so basically what we are concluding is, larger the quantum number of the state, smaller is its population at a given temperature. Therefore, if you are trying to understand that you have a very large number of particles in your system and whether a substantial fraction of it will be present in a microstate, some kind of an alpha, all you have to do is look at what this number is. If E alpha minus E naught by kT is much less than or equal to 1, there will be a reasonable fraction of the population present in that microstate alpha. So, that brings us to this very interesting concept of how you alter the population of energy states with temperature. So, as you understand, the fraction of particles in the ith energy state is nothing but Ni by N, where Ni is the number of particles present in the ith energy state in an assembly of a total of capital N particles. And now, I can write this as Pi by P naught. What is Pi? Pi is the probability that the system resides in the ith microscopic state, and P naught is the probability that the system is present in the microstate having the energy E naught. And we already know that this is related to this exponential function. Now, as I increase temperature, as you see at 100 Kelvin for a simple system like this, where the energy difference is about 0.3 electron volt, initially at low temperature, the fraction of molecules present in the higher energy state is virtually 0. But if you look at higher temperatures, you see about 3% of the population has been transferred to the upper energy state. And this tells me that typically this is the representation of the microstate, dominant microstate at low temperature, while this is the one of the more probable microstates having a particle occupying the higher energy state. But please remember, out of the many particles present, only 3% will be going for this model to the higher energy state. And the applications of such very simple ideas about the temperature dependent population of the energy states in a canonical ensemble, and these ideas have been discussed very nicely by Horia Mathieu in his book on statistical mechanics, and I would encourage you to go back and read a little bit like how one can find out the temperature of a flame, or the emissions, interpret emission spectroscopy and absorption spectroscopy as a function of temperature, or even design things like night vision glasses, which are rather exotic, but has this principle at the core. So, thank you, and we will discuss the applications of whatever we have learned in part 1 and part 2 for the canonical ensemble in the next lecture.